Hello, everyone. Good afternoon. Please join me in hosting Dr. Behrmann today. Dr. Behrmann got his bachelor degree from Witwatersrand University in Johannesburg, and she has stayed there for her master's degree in speech pathology. And after that, she moved to Toronto. I think the weather was better in Toronto, maybe. She moved there and she got her PhD from University of Toronto. She stayed for a few years at Toronto, and in 1993, she moved to Carnegie Mellon University, and she's been there since. It's almost impossible to be a student of vision science and not coming across her work. Dr. Behrmann works with normal people and also patients, and her work encompasses attention, face perception, object perception, word perception, and scene recognition. And recently, she also moved, she studies with different modalities and with different, as I said, different populations. So we are very honored to have you today, and we are looking forward to your talk, Dr. Behrmann.
Thank you so much for that introduction. I hope you can hear me well. We had some technical difficulties in the beginning, but I'm hoping that I'll be able to show you all of the material that I've prepared for this morning. I would have loved to have come in person, but given the circumstances, I'm just happy to be here anyway.
Yes, thank you so much. I will share my screen right now and show your PowerPoint.
Perfect, thanks. We'll have to see how the animations work.
Yeah, so can you see the screen right now? The PowerPoint?
I can.
All right, now I will make it full screen, and my pointer is also visible. Okay, so we can move on.
Okay, do I have screen control?
Marlene, you have to, unfortunately, it's going to be a kind of awkward, so you have to say next. And,
that's fine. No problem.
Yeah.
No problem. Thanks so much for your help with this. Okay, my name's Marlene Behrmann. Today I'm going to be talking about hemispheric organization in humans in the service of visual recognition. I'm at Carnegie Mellon University, but in the summer I'm going to be moving to the medical school at the University of Pittsburgh into the Department of Ophthalmology in the New Eye Institute. Next, please. Next slide, please. Great, thanks. The work that I'm going to be talking today has involved many people. On the screen here are a number of graduate students in my lab: Michael Granovetter, Tina Liu, Sophie Robert, and Nick Blanc. Next, please. Postdocs, Marge Mello, Vlad Eisenberg, and Eris Freud, and my two collaborators. Next, please. David Plaut and Christina Patterson. And I'm grateful to all of them. So to the naked eye, the hemispheres of the brain look pretty much identical structurally. It's really hard to see any differences between them. Next, please. But in fact, next, please. Thanks. There are very small structural differences. I can no longer see my PowerPoint.
Yeah, there's a delay in the internet. Let me turn off my VPN and I will share my screen again. Sorry for that.
Okay. No problem. Okay, good. Okay, so to the naked eye, the two hemispheres of the brain look rather similar in structure, aside from some very small differences, like this Yakovlevian talk. In humans, the right hemisphere anteriorly projects a little bit more forward, and the posterior occipital lobe a little bit more backward. Next, please. There are, however, enormous differences apparently in the function of the two hemispheres. And so the question I'd like to address today is, what are these functional differences and how do they emerge in cortex? Next, please. Okay, the popular press, at least where I am, constantly shows images like this. And the major claim here is that the left hemisphere is more analytical. As you can see in most of these images, it's in monochrome, it's kind of boring and dull, it's calculating, whereas the right hemisphere is very active and very excited. Even in the bottom right-hand corner, you can see, the right hemisphere with people flying kites and just having a really great time. Next, please. Okay, this depiction is a little bit closer to reality in the sense that it picks up one of the apparent distinctions between the hemisphere, and that is that the right hemisphere represents faces and the left hemisphere represents words. Can I have next, please? Next, please. Yeah, so faces on the one side, next please, words on the other side. Okay, but we don't have to rely on images from the popular press. We can actually collect data. Next, please. I think there's a delay. Great. We can put participants in a magnet. We can show them, next please, words, faces, objects, houses, and bodies, and we can see a very standard result that now many people show, in which you see regions on the inferior temporal cortex, which is what I'm showing you here. The occipital lobe is where it says RH and LH, right and left hemisphere. And you can see in red is the so-called fusiform face area, which is selectively activated for faces. There's a visual word form area, areas for houses, a body area, and the LO is an area that's activated by common objects. Next, please. I'm going to zoom in very specifically and look at the fusiform face area and the visual word form area, because these are a really good matched set of categories that allow us to understand this apparent lateralization with faces to the right and words to the left. We are extremely good at face recognition, recognizing something like probably 10,000 faces, and reading at something like 238 words per minute. So these are both domains in which the visual system is just highly tuned and potentially even optimized. Next, please. Okay, there are also good theoretical reasons why faces and words might be represented separately in the brain, why there is a segregation of representation. Please show me the next three altogether. Okay, firstly, faces and words are very different in terms of their input features. Faces are roundish, words are typically made of straight edges. Another theoretical reason is that faces have been around on the evolutionary timescale for much longer than, sorry, back please, than words, where kids have to go to school in order to be able to learn to read. And in fact, in our culture, only in like the last, say, 200 years has the general population had access to literacy. And finally, there are acquisition differences. Babies grow up, they learn to recognize faces, but to learn word reading, kids typically have to go to school and receive a lot of drill on the ability to read. Next, please. Okay, so today I'm going to do three things, and please fill out the rest of the slides for this. I'm going to examine hemispheric organization to, first of all, examine the nature of the organization. Is there segregation? I'm going to argue that there actually is not. And I'm going to propose an account of interdependence where faces and words share similar or actually the same computational principles. And lastly, I'll talk about the plasticity of the system in which there is a malleability of hemispheric organization. Next, please. The first thing I want to tell you and show you is the evidence that people have used to argue empirically for segregation. And in the next slide, we know from neuropsychological data that a lesion to the right inferotemporal cortex can impair face recognition. This is a disorder known as prosopagnosia. And in the left hemisphere, there is an equivalent impairment referred to as pure alexia, in which following a left occipitotemporal lesion, individuals who are premorbidly literate lose their ability to read words. So the neuropsychological data argues for segregation. Next, please. There are also good data from electrophysiology, say EEG recording, and the findings show that I hope you can see in the next slide, I'm still looking at the neuropsychological data, but on the next slide, using EEG, there is considerable evidence for left hemisphere stronger N170 for words and in the right hemisphere for faces. I'm still seeing the neuropsychological data. And to make life easy, I'm going to ask you just to move to slide 18 so that we can just skip ahead. Okay, next. 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 Okay, so there is electrophysiological data for face recognition that's greater in the right hemisphere and word recognition that's greater over the left hemisphere. And there are loads of functional imaging studies that show selective activation for faces on the right and for words on the left. All of these data argue for a segregation between face and word recognition. And this has perpetuated this claim of strong lateralization. Next, please. But if we look a little more closely at the existing evidence, I'm going to suggest to you that the evidence is really against segregation. Next, please. So, for example, yeah, you can put them all up just so that it'll make it easier. If we look at this left-hand corner that says Canwisher et al., you can see that there is a small window over the right fusiform face area. But if you look closely, there is an area that's activated in the left hemisphere as well. And if you look at all of the other images on the left, you will see that there in fact is bilateral activation for faces in almost all of the imaging studies. And if you look at the four pictures on the right, again with the upper left one showing a rectangle around the left occipitotemporal cortex, you can in fact see activation in the right occipitotemporal cortex as well, and the other images as well show bilateral activation. Next, please. In a study that we conducted looking at words and faces within the same individuals, with letter strings shown here in pink and faces in orange, and I'm showing you both the inferior temporal lobe as well as on the sides the flattened sheet of cortex. What I'd like you to pay attention to is that in both hemispheres you see both orange and pink. In other words, there is both face and word representation in both hemispheres. But if you look at the right hemisphere, you'll see the orange is bigger than the pink. So there is greater representation for faces than words. And in a complementary fashion, in the left hemisphere, there is more purple than orange, showing greater activation for words than faces in the left hemisphere. Next, please. Moreover, if you examine, one back, please. If you examine these homologous regions, you see that the coordinates in functional imaging are the same in the right and the left hemispheres. As you can see, the coordinates, 3D coordinates below, show how similar these category selective regions are in the left and the right hemisphere. Next, please. We've also conducted an ERP study in the same individuals, and I'm showing you here bilateral activation for words. So negative is good, so the more blue is better. So bilateral activation for words, slightly stronger on the left, bilateral activation for faces, slightly stronger on the right, at about 170 milliseconds post-stimulus onset, the classical pattern detector at the N170 mark. Next, please. Another commonality between face and word neural representations is that face recognition has a long developmental trajectory. So shown here, if we look at just the adults on the right-hand side, are findings from a study that I did a long time ago in my lab with Susie Schiff. And I'd like you to attend to the fact that the fusiform face area in adults is primarily in the right hemisphere on the inferior surface. And if you look below at the lateral surface, you'll actually see that the right hemisphere has got many sites of activation in red for faces. The adolescents in the middle show a very similar imaging profile, which is very close to that of the adults. But children ages 5 to 8 who are already in elementary school are not showing a fusiform face area. And in fact, we know that the face recognition of children ages 5 to 8 is really not mature, and they make many, many errors in face recognition. So there's slow maturation. Next, please. There is also very slow maturation of the visual word form area in children ages 6.4 to 11.6 years who are already learning to read. We are not seeing anything like the activation in the adults in the visual word form area. And again, I'll point out to you that here in the adults, we can see bilateral activation. Next, please. So I'd like to argue today that instead of thinking about the strong form of lateralization, it makes much more sense to consider the data that is against the segregation. And this leads me to propose an alternative account of interdependence between faces and words. And I'm now going to lay that out for you. So I'm going to do a deep dive into this account. So let's imagine going down into this alternative space. As long as I'm talking about this account, all of my slides are going to have a red border to tell you that I'm still talking about the account. Next, please. Okay, so the first, and you can go ahead and put the next one up. Thank you. So there are going to be 3 principles. The first principle is that both faces and words require fine-grained visual discrimination. The exemplars are so similar. So for faces, everybody's got 2 eyes, a nose, and a mouth in the same configuration. And for words, there are these sort of alphabetic features that are used to generate new words. So both categories require fine-grained discrimination. Next, please. Next, please. And both occupy the anterior extent of the fovea. Can I have the next, please? So in this study that I showed you, we also collected eccentricity data, and this is data from a single participant in which we showed words and faces either in the center of the screen. So I hope you can see that round button that says eccentricity. So blue is central presentation and green is peripheral presentation. And overlaid on the imaging results are the retinotopic boundaries from V1 through to V8, and superimposed on that in an orange outline and a purple outline are the face and word activation of this particular individual. So notice that face and word activation overlay the blue regions, which are central vision. And if retinotopic regions extended into extrastriate cortex, this is exactly where one would expect to find both face and word activation, because you need foveal and very fine-grained discrimination to differentiate between the exemplars. So both faces and words require fine-grained discrimination, you can go to the next please, and occupy the extrapolation of the foveal region into extrastriate cortex. Next please. The next principle though argues, thanks, oh yeah there, the next principle though is ideally, regions of cortex that represent the same information should cooperate and should come to cluster close together, whereas regions that represent unrelated or incompatible information should be segregated. So I'm going to argue that the reason that we see faces and words in the two different hemispheres to a differential degree is because words all need to cluster together and faces all need to cluster together. And this is in fact what we saw on the previous image, where there is this graded asymmetry for faces greater in the right hemisphere and words greater in the left hemisphere, but there is bilateral representation. Next, please. So the third principle, let me show you another example of this coordination and competition. Here are some recent data that we collected in an imaging study. This is flattened cortex in the left and the right hemisphere. And I've marked Broca's area for you in the left hemisphere. These are always right-handers in these studies. The more red something is, the more it represents faces. The more blue something is, the more it represents words. And this again is an illustration of the exact principle that I already showed you, and that is that you get bilateral activation for words and faces in both hemispheres, but stronger in the right hemisphere for faces in red and stronger in the left hemisphere for words in blue. Next, please. And in fact, if we look at the correlation between the activation for words and faces, faces in the right hemisphere, words in the left hemisphere, we see a very nice correlation between them, with the claim being that there is this graded asymmetry. Next, please. Okay, so given the findings that I've just shown you, it's fine to leave it here. With the replication of faces in both hemispheres and words in both hemispheres, you might be wondering, why would we ever see a deficit? So why would we have these neuropsychological cases such that after a lesion to the right hemisphere, they're impaired at faces? Why aren't they using their left face system? And after a lesion to the left hemisphere, they're impaired at word recognition. Why aren't they using the right hemisphere word region? Next, please. In fact, if you look at individual profiles in the sample of 28 individuals, you can see that most of the individuals show bilateral activation. These are now individual profiles. Next, please. But if you look closely, there are individual profiles where you see fairly substantial lateralization. I hope you can see here at the bottom that the left-hand one shows primarily faces in the right hemisphere and words in the left hemisphere in blue, and the bottom right corner again shows this lateralization. I would argue that in the population at large, there are individuals who do have unilateral activation, but most of us have bilateral activation. These unilateral activation people, if they have a lesion to the left hemisphere, they will become the neuropsychological pure lexic patient. And those who have a lesion to the right hemisphere will become prosopagnosic. The rest of us will not. And in fact, both pure alexia and prosopagnosia are very rare in the population at large. Next, please. Okay, so I've told you that both hemispheres are activated for both faces and words, and that there is differential weighting between them. There are, however, some individuals who are more lateralized, but the general population shows this bilateral graded asymmetry. The last principle in this account addresses the question of why is it that words go to the left hemisphere in the population and faces with a graded asymmetry to the right hemisphere? Why isn't it a random coin toss as to which hemisphere these categories emerge in with their graded asymmetry? And I'm going to argue that there is a principle in which there is strong pressure in the brain for local connectivity. Next, please. And this is how I describe this pressure. So initially, when babies are born and then start growing up, there is no initial lateralization. Faces are represented bilaterally. Next, please. But as children learn to read and acquire literacy, I can only see the no initial lateralization. There we go. As children learn to read, so this left extrastriate but foveal region becomes coupled to language areas in the left hemisphere so that we can understand what it is that we're reading. And this optimization of the left hemisphere for word recognition subsequently drives lateralization of faces to the right hemisphere, although this is not entirely binary. There is both representation of both words and faces in both hemispheres, but with this graded asymmetry. And the asymmetry comes from the pressure to keep language and visual areas in the left hemisphere closely coupled. Next, please. So I'm going to show you some empirical data. This is behavioral findings from adults, adolescents, and children. In this experiment, they look at a fixation screen. A face comes up for 750 milliseconds, which is long enough for the children to encode it. Brief fixation, no eye movements, and then a target comes up either in the right hemisphere, next please, right visual field or left visual field, and they have to make a same different judgment. Next, please. Okay, in either visual field, and they make a same different judgment. Next, please. We use the exact same paradigm for word recognition. A word appears, brief fixation, and then a target appears in the left or the right visual field. Next, please. And in fact, you can even go on to the next one. And so we are able to establish the hemispheric asymmetry for faces and words using this behavioral paradigm. That's fine. You can put all the images up. The y-axis is accuracy. And if you look at just the left-hand graph, you can see in adults the standard profile in which face recognition is more accurate presented to the left visual field, i.e. the right hemisphere. And word recognition is more accurate presented to the right visual field, i.e. the left hemisphere. I'd like you also to notice, though, that even for faces in the right visual field, i.e. going to the left hemisphere, recognition is about 80%. So this shows bilateral activation with this graded asymmetry. We see a similar pattern in the adolescents for words, and that is greater accuracy when words are presented to the right visual field, i.e. the left hemisphere. But we are not seeing the lateralization for faces. And if you go to the bottom image, you can see that in young children whose accuracy overall is much lower than the other two groups, they too show the lateralization for words, but not the lateralization for faces. Next slide, please. You can put up the next two. Thanks. And that one. Okay. Back. These findings suggest that there may be an earlier emergence of word lateralization, as I have already postulated, and that it is this earlier emergence, this pressure to read, that drives the subsequent emergence of face lateralization. If we look at the next slide, please, I am showing you here the reading abilities of the young adolescents and the children from the study. And the scores on the x-axis shows their reading proficiency on an entirely separate measure of reading. And on the y-axis is the degree of lateralization for faces. And what you can see here is a nice, significant relationship. So the better the reader you are, the more faces are lateralized to the right hemisphere. Doesn't really matter what age you are. You could have, you could be a red square like the children, or you could be an adolescent. What's really driving this is how good a reader you are, that subsequently leads to the face lateralization. Next, please. Okay, we carried out the exact same ERP study that I mentioned to you before, and we see exactly as I've told you before. Adults show a lateralized N170. I'm showing negative up here just to make it easier to see positive bar graphs. So the N170 in adults is stronger for faces over the right than left hemisphere, and stronger for words over the left than right hemisphere. And in children, which is the critical data point here, we see greater activation in the left hemisphere for words than over the right hemisphere, but no significant difference for face activation. Next, please. Thanks. In some recent computational work, we've explored these three principles in this connectivity constrained computational account of topographic organization. And the organization is really for faces, objects, scenes, and words. The paper was published in PNAS just a couple of weeks ago if you want to consult it. Next, please. Okay, so I have argued in this interdependence theory that there are these three principles: fine-grained foveal discrimination for both categories, dynamics of cooperation and competition that gives rise to the graded asymmetry in the two hemispheres, and finally a strong pressure for local connectivity driving the left hemisphere word activation. Next, please. Okay, so in this last part of the talk, I'm going to ask one final question, and that is this account of interdependence and its emergent organization in adulthood already predetermined? Is this deterministic, or is there some opportunity for plasticity in the system? Next, please. And I'm going to address this plasticity by looking at children with significant brain lesions. But first, I wanted to remind you that in the adult, even with very small lesions, say to the left hemisphere, these patients have puralexia, and it's really hard to rehabilitate them. They don't reacquire word recognition. And on the right-hand side, we see a patient with a lesion to the right inferotemporal cortex who is profoundly prosopagnosic and over many years has not changed his face recognition abilities. So in the adult, even a small lesion can lead to a very significant impairment, which is understandable in terms of these claims that I've been making about this lateralization. And the expectation is that these two individuals are the ones who've got very unilateral representation for faces and unilateral representation for words. They're those small number of rather unfortunate individuals in the population at large. Next, please. I want to contrast those small lesions with the enormous resections that we see in children who have undergone surgery for drug-resistant epilepsy. So these are children with pharmacologically intractable epilepsy. They've tried many kinds of medications and other kinds of treatments. The seizures are not managed, and the surgeons determine that the best option is to remove, in these cases, an entire hemisphere. Next, please. I'm going to show you data from 24 patients with left surgery, so they only have a right hemisphere, and 15 patients who've had a right hemisphere surgery so that they only have a left hemisphere. And the question I want to address is, what happens to face and word recognition in children who are developing with a single hemisphere? Are there opportunities for plasticity and reorganization? Next, please. Okay. Sorry, thanks. The paradigm that we use is very similar to the previous developmental study that I showed you earlier. As you can see, there is a fixation, a word comes up, fixation, and in this particular case, the only difference is that the target word is also always going to appear centrally, so it's in central vision, and then the participants decide if these two words are the same or different, and below you see the paradigm for face recognition. Again, they're making a same different judgment. And by having the patients foveate and view the stimuli centrally, and the controls view the two kinds of stimuli centrally, we can ask what the difference is in accuracy in these paradigms in children who have one hemisphere compared to the controls who have two hemispheres. The second question we can ask is, does it matter if your one hemisphere is just a right hemisphere or just a left hemisphere? Next, please. Okay, here are the results. Faces are in the left graph, words on the right graph, accuracy is on the y-axis. The blue is for the controls and the red is for the patients. If we just look at the blue, we can see that overall, there's actually not that much difference in face and word recognition. So using two hemispheres, you're super good at both face and word recognition. The patients with just a single left hemisphere, labeled patients with LH on the x-axis, and patients just with the right hemisphere on the x-axis, you can see perform equally well as each other, and both are significantly poorer than the controls. And the same is true for word recognition in the right hemisphere. Patient accuracy is roughly about 80 to 85% relative to the kind of 96% that we see in the controls. I've also mapped age here in different color dots. The lighter dot, the younger a patient, just to show you that this isn't entirely contingent on age and what of the patients or of the controls really. And what's really important here, can I have the next image please, is that patients who develop with just one hemisphere show reduced face and word recognition, maybe up to 80%, relative to age and sex-matched controls, etc. The other point that these findings suggest is that there is no difference in a single hemisphere as to whether the patients are doing face recognition or word recognition. So patients with just a left hemisphere are about 80% accuracy on faces, about 80% accuracy on words, and the same is true in the right hemisphere. It also does not matter which hemisphere is removed. These four red bars are all equal to each other and there are no significant differences. Next, please. What I haven't shown you, though, is the mechanism that I have suggested, and that is that there is competition and cooperation across the two hemispheres in the normal population. And now the question is, do we see these same kinds of competitive and cooperative mechanisms just in a single hemisphere? So I'm going to, in these last few minutes, show you some longitudinal data from individuals. As you can see on the top here, this is patient TC, who has a left hemisphere resection. Her first seizure onset was when she was 7 years old. She went to surgery, and I'll show you a little bit more about that in a moment. And we scan pretty much every 6 months moving forward. The second case is a patient UD. He has a smaller resection. It's in the right hemisphere. His first seizure was when he was 4 years old. He had a tumor that's not a tumor that does occur in kids. It's rather rare, but it does occur. And again, he had surgery when he was 6 years, 9 months, and we scanned him every 6 months from then on. So let me show you what it looks like longitudinally. Next, please. Oh, these are just to, if anybody wants to know how we can guarantee data quality over these many sessions over years, I can share some of the details with you. Suffice it to say that we have good control of TSNR. Next, please. We have good control over head motion. Next, please. So I want to first show you the control data. This is over 26 individuals. We actually have very many more now. What's difficult about this work is that when the patients are, say, 7 years old, we have to get controls at 7 years old. And then when we scan them when they're 9 years old, we have to get a new set of controls at age 9. So I just want to show you generically what normal controls 2 hemispheres look like. Next, please. And they basically show the pattern that I've been talking about. And that is that you see bilateral activation for faces and bilateral activation for words, which is in orange. And actually, for words, we do typically see stronger left hemisphere activation than we see right activation for words. And that's exactly what we see here. Next, please. Okay, this is patient TC. I just wanted to show you that we collect data off grids prior to the resection, and the neurologists map out language and motor regions, and then the patient goes to resection. These patients are almost all hemianopic. We never see mapping of early visual cortex, sort of retinotopic cortex, to the ipsilateral hemisphere. These days, we also collect data from depth electrodes rather than using grids. Next, please. Okay, so this is one of the 2 patients. This, in fact, is patient UD. We scanned him over these 4 different sessions. Next, please. And I will just show you with these arrows that face activation in his single left hemisphere increased over development, and we also see an emerging close by word activation that is also emerging over development. Next, please. In order to understand this developmental profile in more detail and to examine this competition, I hope you can see here in D, these are the 2 hemispheres. You can see the resection in the right hemisphere, which is basically scooped out occipital and temporal cortex in the right hemisphere. So over his left hemisphere extrastriate regions, shown here in blue in D, and then in 3D in E, we're going to specifically zero in on this volume. And I'm showing you the volume in the cubes below. 1 to 4 in those different plots shows every 6 months over longitudinal development. So if we go to CL1, which is on the left-hand side, and we look at that volume, this is every voxel in that volume. The stronger the red is in a voxel, the more that voxel is face selective. The more blue the voxel, the higher the word selectivity. So you will see in both CL1 and CL2, there's not a strong red nor a strong blue. They are pretty uncommitted voxels. But as we get to CL3 and strongly in CL4, we see that in neighboring regions in a single hemisphere, there is some separation between face selectivity and word selectivity. They come to occupy, faces comes to be clustered, words come to be clustered, but in the same cortical region that I have been showing you over and over again in the single left hemisphere. And we see this graded change over time with the microgenesis of this competition for neural representation in the region that allows for foveal vision in the single left hemisphere. Next, please. Okay. This is patient TC. I showed you her surgery and her brain open. What's particularly interesting about her is that she's got a left hemisphere resection. So she only has this cortical crucial region in the right hemisphere. And again, over time, we see the pink getting bigger, so face representations in the right hemisphere. That's not surprising. And we're also seeing the emergence of a visual word form area in orange, as you can see when she's about 15 years old. She has a very slow developmental trajectory. Actually, English was not her native language, and so it's not that surprising that it's taking a long time for word selectivity to emerge. Next, please. And we can zero in on that same volume in her preserved right hemisphere. And here scanned over 3 different times, if we look at that volume, we see a very similar pattern, and that is when she was already age about 13 is the first CL1, category localizer 1, in which we already see some face selectivity in darker red and a few red and a few dark blue voxels. And again, over time, we begin to see this abutting but clustered segregation of voxels in a single hemisphere for the representation of words and faces. Next, please. Okay, so let me sum up what I've told you. The goal here has been to uncover the topography or the hemispheric organization of the cortical extrastriate region in humans, specifically in the service of complex pattern recognition for words and for faces. I started off by showing you a lot of evidence which has supported the idea that face and word recognition are lateralized and entirely segregated. And I went on to argue against the segregation by showing you data that not only do we see bilateral activation, but we do see some graded asymmetry with greater superiority for faces in the right hemisphere, but also word recognition in the right hemisphere, and graded asymmetry for words in the left hemisphere, but also some face recognition. I then tried to offer an account of interdependence in which face and word recognition emerge through competitive and cooperative interactivity and the pressure to be coupled to language regions in the left hemisphere. And last, what I showed from children who have these very large resections is that there is the opportunity for plasticity and potential reorganization in a single hemisphere. And in fact, longitudinally, we see something of these competitive and cooperative effects in which the representations come to be adjacent and abutting, but with some preference for one of the 2 categories. Next, please. So I'd like to leave you with a final message that is there is no obvious binary segregation of these 2 categories in ventral visual cortex. And images like this that are perpetuated by the popular press are entirely dissatisfying and inadequate. And my hope is that as we move forward, the popular press may be able to take on a more complex and nuanced view of the segregation of the hemispheres, or the lack of the segregation of the 2 hemispheres, the more distributed and weighted asymmetry account. Next slide, please. So and here is my little depiction of both hemispheres having both left and right so-called components. So some left hemisphere capabilities, so-called left hemisphere capabilities in the right hemisphere, and some so-called right hemisphere capabilities in the left hemisphere. Next, please. So I'm going to end off here by once again thanking, you can show them all, thanks, thanking all the people in my lab who have done all this work, and the National Institutes of Health and National Science Foundation for their ongoing funding. And if you go back one slide, please. And I'll leave up my final summary and next one, please. Oh, back, please. Yeah, and you can just put them all on. Okay, so this is my final summary and I leave it here and am happy to take questions. I apologize again for all the technical difficulty. It's actually worked a little better than I was expecting, and thanks very much to Ali for managing my slides on that side. Thanks, I'll take questions.
Thank you very much for the great talk. We have a few minutes for questions before we move to the panel. Guest number 5, asking 2 questions. He asks, I'm reading it for you. Is face word lateralization more pure and perfect when the person has started reading at earlier age?
Oh, it's an excellent question and an important question about age. If we go back to slide, I've got my slides up here as well, and I'll tell you. Yeah, that you're very close. No, down, down, down. It's like the violin plots that keep going. It says slide 55 for you. Yeah, great, thanks. This shows age, which is in these different color dots. The lighter a dot, the younger the controls, and the younger the patients as well. In these results, we do see an effect of age. I haven't exactly shown it to you here, but you might notice that if we just look at the patients in these red bars, there are more darker red circles than there are lighter orange circles. And this is the age effect that you're referring to. So it's not the age at the surgery. It's not the age at the first seizure. It's just their absolute age. They all had surgery in childhood, but some of these individuals are now 13 and some of them are, say, 9 years old. So the younger you are, the less developed you are. But it really is not about the start of the epilepsy nor the time of the surgery. And so I don't think it's about the purity of the representation or the fine precision of the representation. This is really the normal course of development in epilepsy children that we typically see in normally developing children as well. I hope that answers the question.
He had another question. He asked, is the localized activity more pronounced when the task is active rather than passive?
Yes, definitely so. These are all task evoked, so they are always performing a word discrimination task or a face matching task, something like that. We know from many, many resting state studies that we can get activation, but it's nowhere as strong as when we have them on task, paying strong attention and making some kinds of judgments.
Okay, thank you. Dr. Ghazizadeh, please go ahead.
Okay, thank you, Marlene, for the great talk. So I have a quick question too. So I'm not sure if you showed this, but is there any correlation between the amount of lateralization in face and in word processing? Did you ever show a plug like that?
I did show that, but I'm very happy to show it again. So if you can go back up, go up, further. Oh, you're very, no, sorry, go down a little bit. You're close to that. You can, a little bit more, I think. Yeah. No, keep going. Sorry, maybe I'm going in the wrong direction. Let me just consult my slide here and I'll tell you which number it is. It's number 37. Yeah, there it is. Okay. So this is the correlation between the strength of word activation in the left hemisphere on the x-axis and the strength of face activation in the right hemisphere on the y-axis. And across these 28 individuals, we see a nice correlation in the magnitude of the lateralization. But notice, while I'm here, notice that many dots are clustered in the bottom corner. And so they are very similar in terms of the lateralization in the two hemispheres. So there are many who have kind of equal lateralization, and then some more extreme ones.
And I guess from your other plot that you were showing the correlation between the expertise in reading
Yes.
and lateralization, one might conclude that the more lateralized you are, I mean, the lateralization gives you more of an edge, basically, like a skill.
Yes. So this is slide 45. I think so if we think from a kind of computational efficiency perspective, lateralization does give you an edge, one might imagine, because you can let the representations be segregated and they can all develop to their optimal without any interference. On the other hand, we might also want to build in a bit of redundancy into the system so that if something does go wrong, you can always rely on the other hemisphere. It may not be as great, but we can see here, even in the young kids, that a single hemisphere actually is reasonable. It gives you about 80%, not 50% like you would predict if you only had a single hemisphere. Here you get more bang for your hemispheric buck. And so lateralization is good, but it's not so great. There are reasons for us to have duplication in cortex.
Have some redundancy so you can basically
Exactly.
Right?
Exactly.
Thank you.
Okay, guest number 5, please. I'm giving you access to your microphone. You can ask your question. Guest number 5, you can open your microphone and ask your question. Okay, probably he doesn't have any question anymore. So,
okay.
Any other questions? We have time for one more question before we move to the panel. I have a question. You mentioned that in the word left hemisphere become representing the word more because it's closer to the Broca center, and also
Correct.
So what we know that a few percentage of people has a language center on the right hemisphere. So do you see that this kind of what happens in the brain of those people?
Okay, it's a great question. I should maybe have made this one point a little bit more clearly, so I'm grateful for the question. All of these individuals are right-handed. Mm-hmm. And in right-handed individuals, almost everybody has got left hemisphere Broca. Yeah. There are some left-handers, a very small percentage actually, that have right hemisphere language areas. Mm-hmm. For the majority of the population, the argument about coupling of Broca's area and visual areas in the left hemisphere holds. Mm-hmm. I have published a paper on what happens to individuals who are left-handed, some of whom have got left hemisphere Broca's and a few have got right hemisphere Broca's. Some have got both actually. We see the emergence of the visual word form area in those with right hemisphere Broca's in the right hemisphere, which is also true for these epilepsy children who only have a right hemisphere. Language emerges in their right hemisphere. The visual word recognition is in their right hemisphere, so coupled to Broca's area, and then they have face activation in that same region as well.
Okay. Thank you. Thank you very much. Thanks for the great talk, Dr. Behrmann. And
Thanks.
I
So
invite
now I'm going to go
you,
to the panel room, right?
yes, please. And everybody,
Okay.
please join us in the panel, and
Thanks
it's more
very much.
informal discussion we can have there.
It was my pleasure to talk here today.
Thank you.
Thank you.